All right, this is Dr. B, and welcome. It's Tuesday again, and here we are going to do some chemistry tonight. For the folks that are here, say hello in the chat so I can see who's here with us tonight. Right now it says there are 7 people here, but that's always a little bit delayed. So tonight what we're going to do is we're going to look at some just general chemistry, some organic chemistry, and we're going to focus on just one molecule. And we'll look at molar mass, moles to grams, molecular geometry. And that molecule is this one right here. So that's what we're going to work with and use that kind of as our model to learn a bunch of chemistry. So I've been working on the chemistry application, the web application, and if you look in the chat, I pinned the URL. So you're welcome to check that out. I haven't done much work on the actual adding more content, mostly trying to build the back end. And I wanted to show you something else I've been working on, if I can find that here. Where is it? No. Okay, let me, over here. This took me a while and I'm kind of proud of it here. Let's see if you can see me or my screen. Here we go. So I built this the other day. This is my front yard here in Rockville, Maryland. And this is a snowman that I built. I put a little blinking light right there in the heart for the snowman. So that's the other thing I've been up to. It's very cold here in Washington, D.C. It's warming up now, but it was really, really cold. We got a lot of snow. So kind of fun there with that. So let's do this. Let's do some chemistry here. I see in the chat, Bryce is there. Andy, good to see you, Andy. And Loretta's there. Awesome. So got a bunch of folks with us here tonight. So we're going to start out with just naming this compound here. And so it's kind of some organic chemistry. And how do you name the compound here? So give that a try. And while you're naming that compound, I'm going to write the carbons in just so you know where they're at. And be careful because there's no carbon here. It's just the oxygen. But we have carbons here where they just end like that. So how do you name this compound? And this OH group here is real important. I can see right now there's a lot of latency in the stream. Like I'm watching the stream that you're probably seeing right now, and it's me talking and it's like in slow motion. So how's the health of the stream? What are you guys seeing out there? All right, so we want to find the longest chain. That's the first thing that we do. So if we started counting carbons, we'd go 1, 2, 3, 4, 5, 6. So 6 carbons. You could count it 1, 2, 3, 4, 5, 6, but we want this to be on the carbon with the lowest number. So 1, 2, 3, 4, or 1, 2, 3. Let's start here. Hexabutyl, no, not quite. Thank you, Loretta. That's good to hear. Oh, Bryce sounds good. Okay. It's kind of weird looking to me on my monitor. So we start here. 1. Oh, there's a carbon there. 2, 3, 4, 5, 6. And on the 3rd carbon, we have that OH group. So we're going to call it 6 is hexane. And then because we have the OH group here on the 1, 2, 3, we're going to call it 3. Take this ending off here, and that OH means it's an alcohol. So 3-hexanol. That's what you would end up calling this. Oh, we forgot our methyl groups though. So 2, 4, wow, 2, 4, di, I need more room. 2,4-dimethyl 3-hexanol. Something alcohol. Alex, you've got it. It is a something alcohol. So I actually have the names here for you. 2,4-dimethyl 3-hexanol. And sometimes you'll see it written like this here. This is kind of the more IUPAC name. This is mostly what I see, but same setup there. So that's how you name that compound there. Find the longest chain, write your numbers, and then put your groups on. Since it's an alcohol, we got that OL. All right. So let's take this and write the formula, like C something, H something, O something. Can you write the formula for this compound? Because that's not that easy. I'll write the carbons back in. Carbons, carbons, carbons. So CH something. Here's the thing you need to realize. Each carbon is going to have 4 bonds. So this carbon has just the 1 bond. So we're going to put hydrogens here so it has 4 things bonded to it. Here we have 1, 2. So you got to put those hydrogens there. So these each here, these will all have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Here we have 1, 2, 3, 4, 1, 2, 3, 4. So if you can remember that carbon always is going to have 4 bonds. It could be a double bond, that would count for 2, or here we just have single bonds. So C8, 1, 2, 3, 4, 5, 6, 7, C8, right? And then you got to count all the H's up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I forgot one right there. 12, 13, 14, 15, 16, 17. So you could call it C8H17, and then we have this OH. And I would just put that on the end, because that lets you know that it's an alcohol. If I see this, I know it's an alcohol. Is that right? Yeah, that's what I got before when I did it. So often you'll see the OH on the end, and that'll just show you that you have an alcohol you're dealing with. Let's take a look at this in 3 dimensions here. So I'm in a program called MolView that I'm doing this. You got it, Bryce, that's right, but you don't need the dash after the 17. So this is called MolView. It's just molview.org, and I can go to 3D. And we really can see now how each carbon has 4 things bonded to it. Like this one, 1, 2, 3, 4. You see the hydrogens? And then up in here, this one has a carbon, a carbon, a carbon, and a hydrogen. So this is kind of helpful to really see where those hydrogens are around there. And they take up space. So all of this stuff, because of that sp3 hybridization, has that kind of bent look to it. Yeah, so kind of fun to look at that. All right, let's go back here and take a look at finding the molar mass. And actually, you have to have a periodic table or memorize things to find the molar mass. So carbon is 12.01 grams per mole. Hydrogen is 1.01, and oxygen, typically we say 16.00, and all of these are grams per mole. See if you can find the molar mass for this. And we said it was what? C8H17OH. I think that's what we said. So give that a try. Thank you, Colin. So let me guess, Colin, you are in Ottawa or Chicago or Bellingham, Washington. Am I close? Dr. Face Reveal. Yeah, I don't usually show my face a lot. I mean, I don't know, it's my face, right? But yeah, typically in my videos, you'll rarely see me on my YouTube channel in my videos. And so, Colin, if the reason I can tell where you're at is the app I have, I'll pull it up here. It has a map of everybody. So someone's from Ottawa, that's me in DC, Chicago, Hill City. So I can see kind of on my map who's using my app, which is kind of fun. All right, let's do that molar mass there. All right, so when you do the molar mass, it's pretty much multiplication and addition. The thing you really got to remember, though, and students always forget this, the units are grams per mole. And so when you're doing calculations, you really need to have that. So the way I would work it out is I would write 12.01 for the carbon, that's its molar mass, and that's right off the periodic table, times 8 plus, what do we have? 1.01 times 17 plus 16.00 plus 1.01. And if you add it all up, you'll get some grams per mole. And that something is, I see 129.25, 121.17. I got 130.2 grams per mole, but I could have done it wrong. So I'm going to say we have 3 significant digits, so I'm going to say 130.2, but you guys might be right. I might be wrong. Looks like it should be an even number. Iowa. Yep. I actually, my wife is from just outside Des Moines, Iowa. So I've been to Iowa many times. It is too cold. Yep. And I will, I leave all my videos up, so you're welcome to go back. Egypt, translations. What language do people speak in Egypt? I don't know. Probably several languages. I'm not sure. I've never been to Egypt. Okay. So you should be close to this 130.2 number here, but that's how you do molar mass, and you end up doing that a lot in chemistry here. I like polarity. So is this a polar or non-polar molecule? And I've given you a little help here. I don't know if you can see it though. Make it a little bit bigger here. Move it down here. Polar or non-polar. Here's your, whoops, I just turned that upside down. Okay. Here's your oxygen, carbon, and hydrogen, and these are our electronegativity values. Arabic, okay. Yeah, Andy, those H's are tricky. I even almost didn't write the one in there. So Indonesia. Awesome. Polar. Well, how do you know it's polar, Alex? That's the big question. It kind of is a bit of a giveaway when you look at it. The key here is we have oxygen is 3.44. That's its electronegativity value. And the carbon here is 2.55. So as long as this difference is over 0.5, the difference is greater than 0.5, and less than 2, because that would be ionic, right? 2.0 would be, above would be ionic. This is a polar molecule. And because of that alcohol group, right, exactly. You see that oxygen and the hydrogen, you know it's going to be a polar molecule. Let's look at this in 3D again, because that really, I think that helps people understand. Oh, that's not it though. Where did it go? There it is. So what I can do with this program, it's a free program, moleview.org, is I can go up here to JMOL and show you the surface. And this is going to show you the electrostatic surface. That means kind of the electron density, and more density would give you a negative area. I'm going to turn this off here, make it a little smaller. So now you see that all the green is non-polar, but look at that oxygen there. See that red? And then the hydrogen, that's going to be positive. So we have a negative and a positive. It's definitely a polar molecule. And Pavel, you're asking why the numbers are different? It's just because chemists kind of made them up for convenience. When you look at any compound, like with this, we say that it's a covalent molecule, but it does have a little bit of ionic character because of the polarity. So polarity is a continuum. And because of that, they just kind of chose values that seemed to make sense, but people chose different values. So it's just kind of a convention type thing. It's a good question. All right. So definitely going to be a polar molecule here, but there's a lot of nonpolar aspect to this as well. All of this is nonpolar here. So that's our alcohol. We'll come back to this in a minute and look at what that means when we put this in water. All right, here we go back to, let's look at our map here. We have 8 people using the app. Now we have someone from, what country is this? Whoa, what just happened? Croydon. And then someone from Kathmandu. Oh yeah, you were here last time. I remember that. Kathmandu. Very cool. All right. So let's go back here and go down here. So definitely a polar molecule, but is it miscible in water? So is this going to dissolve in water? That's what I want you to think about. And remember, water is a polar molecule. I'm going to pull water up here to show you what water looks like in mole view. Make it large. So if you're looking at water, kind of pretty. This is what water looks like in terms of polarity. Negative up here, and then these are going to be kind of the positive side of water. So it's really a polar molecule. All right, so there you go. All right. Hello, Dino. Good evening, Ramana, or good morning, Ramana, for you. How do I bond the molecule on the website? I'm not quite sure, Alex. That's a good question. So when we talk about miscible with alcohols here, we talk about will they dissolve in water? And when you look at the polar part, you're thinking it will, since water is polar. But most of this molecule here is nonpolar. So we have mostly a nonpolar molecule. So this is what we call immiscible. It won't dissolve in water. So for alcohols, if you have 3 carbons, like propanol, that would be miscible. Maybe like 4 to 6, slightly. And then over 6, it wouldn't be, it won't be miscible. So it won't mix with the water. Maybe it'll make the water a little cloudy. Oh, I'm almost out of storage, evidently. There we go. But we say that it's immiscible. So when I was a student, when I was in college or in high school, I would have said that this would dissolve in water. But now I understand that all of this is nonpolar. So the water's, it's just not going to dissolve. So kind of an interesting thing. And sometimes they'll ask that on questions that you have something like an alcohol with 5 carbons, will it dissolve in water? And you might say slightly. Or if it's over 6, you say it wouldn't. All right. Yeah, Bryce, you're probably right. I mean, if we look at solubility, everything's a little bit soluble or miscible. So a little bit probably would interact with the water, but not much at all. And as you add more carbons, even less. All right. Let's take a look. Oh, this is fun. This is I have to be honest that I tried to do this really quickly and I did it wrong before the stream and had to figure it out. So see if you can balance this equation. And the hint I will give you is, since you have O2, just oxygen here, do the oxygen last. And probably start with carbon. So I'm going to give you a moment to at least get started on this, and then we'll talk about it. So Matthew, you're talking about neutralization. Let me search over here on my videos and see if I can You're talking about rearranging the formula on the product side when you have neutralization. Okay, let's see if I can find a video for you over here on my website, on my channel. That might help you. See if anyone can balance this equation. Oh, I did a stream on neutralization, actually. That's interesting. All right, Matthew, I'm putting this in here, the chat. This is a stream I did on neutralization one evening. So that might help you. All right. Thank you, Adam. All right. So I'm going to start trying to balance this here so you can see how I approach it. But if you're doing it, you don't have to look at me. You can keep trying to do it. I like to think like an accountant and keep track of everything, especially with this. Exam Friday. Well, good luck with your exam. The best luck with that there, Adam. What's your exam on? Let's do the carbons first. Oh, I have to count all these up. So I'm going to say 8, 17 plus 1 equals 18. 1 plus 2 equals 3. 1, 2, 2 plus 1. Put an 8 there. Now, so what I've done is I started with the carbons, and then once I did that, I had to update the oxygens. But I'm leaving this side here till last, so now I'm going to do the hydrogens. Bryce, you might be right. If you are, that's impressive. So here, I'm going to put a 9. 2 times 9, that's 18. So now, all that's left is the oxygen. And the way I think about this is I need to have something to get me to 17 here. So I need to get to 17. So I could say, if I put 8 here, that would give me 16. 1 plus 16 would equal 17. Did I do it right though, Bryce? It doesn't look like I have it. I don't think that's right the way I've done it. Let's think about this again. Do I have 17 over here? I do have 17. So I have 1. I think I'm doing something wrong. Oh, I added my oxygens up wrong. That's why. 8 times 2. You all got to help me out. Yeah, I think you guys are right there. So 8 times 2 is 16, plus 9 times 2 is 18. Is that right? No, 9 times 1, because we only have 1 oxygen. So we have 25. So that makes sense, because if I had 12 here, plus the 1, that would give me the 25. So Bryce, Romana, you guys are actually better at this than me. So congratulations. Yeah, and so that's what makes it tricky though. But if you leave the oxygens till last, that's really kind of the way to manage these combustion reactions. All right, where are we at here? Why don't we play with some primary, secondary, and tertiary alcohols, because that always comes up on mainly on organic chemistry, but sometimes in general chemistry. So is this a primary, secondary, or tertiary alcohol? That's the question. I even gave you this little thing here. Whoops. Yeah, Bryce, I think the challenge is once you can balance equations is to then apply them to the stoichiometry. And the way to really think about the numbers that we got is as ratios. and you can think about them as ratios of moles or molecules. But when I balance an equation as a chemist, a practicing chemist, it's the ratios that then let me predict, if I start with a certain amount, how much I'll get or how much I'll need for the reaction to be completed. And many students don't ever understand that when we're balancing, we do want to obey the law of conservation of mass, but really we want the ratios so we can solve stoichiometry problems. So that's the next big step for you there, Bryce. Get those stoichiometry problems. All right, so what do we got? Primary, secondary, or tertiary? So when we're talking about it with alcohols, it's always in respect, relative to the alcohol group. So here we have a carbon attached to a carbon, and then we have our oxygen. So here's a carbon, carbon, oxygen. So it looks to me that that's going to be secondary. That makes sense to you guys? Let's try another one. Because typically that's what happens. They'll give you something like this and ask you to figure it out. I think over here, yeah. So this one's a little more, this has two types of alcohols. So it's going to have two of these up here. Two types of alcohols. So let's call this number 1 and number 2. Oh, we now have someone from Yuba City on our map over here. 9 people are using the apps, counting me. So kind of interesting. People are doing that instead of watching the stream. They're like, that's more fun. All right, so let's try this one. You should see right away here, you just have attached to the carbon. So this is a primary. You can even just write it like 1 with a little degree symbol there. Here we have 1, 2, and then like this here. So we have, here's our OH, and this carbon has carbon, carbon, carbon. So this is a tertiary alcohol down here. Oh, internet is unstable. Sorry about that, Galaxy. I can't quite tell what's going on. Probably too many people are on my stream. There's 22 or so right now. I'm being a little facetious there. Is anybody else having problems with the internet connection? All right, well, let's try one last one here without the chart. Let's move it way over here. What type of alcohol do we have for this one? Running smooth. Mason says I'm good. Omar, organic chemistry is, I don't think it's that bad. It's just a lot of content. So organic chemistry is the type of thing where you just keep getting more and more content and it piles on itself. You have to be able to name everything. You have eventually get into reaction mechanisms. And the other thing is you have to really visualize stuff. Like the program, that moleview.org program I showed you, that's really helpful for visualizing. So I think it's more that it's just a lot and you can't fall behind or you have problems. This is the website I was using to show you these 3D structures. So this one here is, we have 1, 2 carbons attached to it. That is our secondary then. So hopefully that helped. If you search on primary, secondary, and tertiary alcohols, you'll find, this is from a video I did on that. Hello, Wissam. Thank you, Andy. Good to know that I'm running smooth, at least some places. All right. So for this problem here, you always get these moles and grams problems, and they make chemistry students a little bit crazy, but they're not too bad. The thing we do need to remember is that molar mass. So let's 130.2, I think. That's what I had there, grams per mole. So how do you get from grams first to moles, and then how do we do it to molecules? Yeah, you're right, Alex. You have to learn that nomenclature to use the website. Eventually, I'd like to put videos, more videos. Some of them have videos to help you with that, but I'm hoping to add more content to it. Mostly right now, I'm trying to figure out how to do all the programming in PHP and all kinds of stuff, CSS, HTML, that I kind of know, but I'm learning. So, we're all learning something, right? Trying to struggle along and learn. So remember this, if you're going from moles to grams, you multiply by, I'm going to just put the molar mass here. So if you can remember that, you're in good shape, right? Because moles to grams you multiply, grams to moles you divide by the molar mass. So we take our grams, 7.23 grams, and we're going to divide that by the molar mass. 2, and remember those units, grams per mole. And if you follow your units, grams cancel out, you're going to be left with moles. I don't know if anyone did that math yet. Thank you, Rita. It's great to hear that you're using my videos. I do appreciate that. That helps me a lot. I end up with 0.056 moles. So remember, moles to grams multiply by the molar mass. Grams to moles, you just divide. And you make sure the units cancel out, and you're good. The other side of that is, how do you get this moles to molecules? Let's move up here, because we don't really need the rest of the question. And this is kind of like an AP question. I asked ChatGPT to write an AP question, and it gave me something like this, and then I modified it to be closer to what I like. So moles, right? Whenever you're going from moles to anything, you multiply. So I'm going to multiply by Avogadro's number here. And let's see. I want moles to cancel out. So yeah, I'm just multiplying. We have 1 mole is 6.02. Make it look like an O. 02 times 10 to the 23rd molecules. So again, I'm multiplying because I'm starting with moles. Those cancel out. We're left with molecules. And I get 3.37 times 10 to the 22nd molecules. All right. I probably won't do organometallics in the coming days just because I haven't done that for a while. So I really stick to stuff I'm really good at. So you're right, Andy, Avogadro's number there. Yeah, that is, Omar, that is challenging. I agree with just remembering all the tests, and that's a lot of memorization to do that. So the key here, right, if you're going from moles to anything, whether you go from moles to grams or moles to molecules, you multiply. Here we multiplied, here we divided because we started with grams. And here we ended up with our molecules. Things cancel out. You're in good shape. Let's, I don't know if do I have any more here? I was a little bit ambitious here tonight as well. How about this? Molecular geometry. I love molecular geometry. What is the molecular geometry of let's say with respect to this carbon right here, they're all the same actually. What is the molecular geometry of this carbon? And then we'll look at this oxygen. So 1 and then 2. Can I explain ionic equilibrium? I probably can, but it would take a while. I'm really not prepared this evening to do that. Whenever I have to teach something, I want to have examples, I want to have graphics and so on. So maybe in a future stream, though, I will do that. All right, molecular geometry. So you kind of can use the chart I have here, right, to look at this. If we looked at this carbon here, you could see there's 1, 2, 3, 4 things attached to it, and there aren't any lone pairs. So it is going to be tetrahedral. So all of these carbons here are tetrahedral. Some people use what's called the AXE notation. And so for the AXE notation, you say A is the atom, X are the number of things bonded. They can be atoms or lone pairs. So 1, 2, 3, 4. And E, those are the lone pairs. We don't have any, so we wouldn't write that. And if you looked up AXE on Wikipedia, it would be tetrahedral. So let's look at that. Let's look at that shape here. I'll put this in the chat. This is the app I'm using to visualize these shapes here, molecular geometries. So I'm going to take, let's get rid of these. Here's my carbon. So I add 1, 2, you see how they spread out. That's their valence shell electron pair repulsion. 3, now you got a trigonal planar here, but I add that 4th hydrogen, and that puts us in this tetrahedral. And the bond angles, 109.5 is the general bond angle. So real helpful to do that. All right. So let's go look at that other part there, that oxygen. That's a little tricky. I don't know if anybody got the molecular geometry for the oxygen there. I'm going to blow it up a little bit. Oop. Let's move it over here. Hey, thank you, SeamJ35. When I started doing videos for my YouTube channel, I really did balancing. I probably got 500 balancing videos, and that means really, I really probably have more than that. I like balancing equations. I don't know why. So we're looking at this oxygen here, and what you need to know here is that there's a lone pair here and here, because remember, carbon has to have an octet. So it has electrons, a pair of electrons in this bond. A pair is shared, one from the hydrogen, one from the oxygen here. So we have these 2 lone pairs here. So that comes into play when we try to figure out the molecular geometry. These occupy space, so they're going to push stuff around. That's why that hydrogen's pointed down. The red of the site that I'm using right in a moment with this one right here, that's the one I just put in there. It's a very useful site. So let's build that. Let's say we have, what does that look like there? We have a carbon. We have one carbon here and 1 carbon here. Here's our how do we think of this? Here's our oxygen. We have 2 lone pairs and 2 things attached. So there's 1 thing, 2 things. You get linear. Now we put a lone pair. Watch what happens. It pushes everything down. So these lone pairs occupy space, and we put another lone pair, pushes it down a little bit more. So this is going to be your bent molecular geometry. And for water, it'll be 104.5, I think. But so when we look at the molecular geometry of water, you got to count these lone pairs. So this is what we call a bent molecular geometry. If we go back and we look at our table, we see the bent here with the 2 lone pairs. So we have 2 lone pairs up here, and then we had 4 things. We had the carbons, the hydrogen and then the two lone pairs. So that's where that bent comes from. And you could use the AXE notation as well to do that. So is there anything else down here? Or was that it? I think that's all I got together. Yeah, so we did a lot of stuff. So use those tools, that mole view, that PHET, that simulation. Try to get the visual understanding of the shapes of these molecules and how they have a surface, and that surface can have different electron densities to cause polarity. Those things, especially in organic chemistry, when you start visualizing that rotating molecules, that helps you a lot in understanding how they interact and so on. So kind of a key part of learning is in chemistry is being able to visualize things, which is a skill. You have to learn that. What is a chiral center? So with molecules, that's a good question, Yash. And we were talking about visualizing, right? This is one you really have to visualize. So the example you'll always get for chirality or enantiomers or stereoisomerism is gloves. Like if you have a pair of gloves, they're not identical. Or if you're reading text in a mirror, it's not identical. It's a mirror image. You can't lay it on top of itself. And so we have molecules that are the same way. You can't superimpose them on top of each other. So that becomes a really big task of visualizing things. And so we have a way to name them. We have R and S, kind of right-handed and left-handed designations. And the way to learn about enantiomers and chiral centers is to get some molecular models like here, like these up here, and actually build them and compare them and rotate them in your hands so you can get that sense. It's not easy though. It takes some practice. Very cool. Well, I think that's it for me this evening. I'm going to wrap up here, and can I explain catenation? Probably not, Arthur, probably not really quickly. I'd have to think about that, how to really explain it. I will be back on next Tuesday, again at 8:30 Eastern Standard Time. Thank you, Loretta. If you have a chance, check out that app. Right now there are people from all over the world. And we have someone from Poland, Wodzinslaw. Interesting. So check that app out. That's at the top, pinned in the chat. And yeah, so thank you very much. This is Dr. B. And as always, thanks for watching. I'm just looking up here. This looks like all these people are studying together here in Michigan and Spencerville. Spencer, maybe they're all in the same room there. I don't know. All right. Yeah, thanks, Alex. Thanks, Anthony. All right, MVLZ123, thank you. All right, good night there, Galaxy. I don't know if it's night in Myanmar, but either way, have a good one. Take care, everybody.